Welcome everybody to another video lesson. Today we're going over solving trigonometric equations. We're going to be able to solve these trigonometric equations as well as find some extraneous solutions. So let's hop right into our concepts. What is a trigonometric equation? Well, previously we were looking at identities. Now the difference between an identity, because an identity is really a specific type of equation. And an identity is a specific type of equation where it is true for every single value of x or theta or whatever my variable is. Now for a trigonometric equation, well, that is a more general term where we have an equation that is only true for specific values of my variable. Okay, certain values of my variable where that's true. So for instance here, I've got sine 2 theta is equal to 2 sine theta cosine theta. Now we can see here I have what looks like one graph, but if you look really close, I actually have two graphs laid over the top of each other. The red graph, which is a little bit harder to see, is y equals sine 2 theta. And the green dotted graph that's over the top is y equals 2 sine theta cosine theta. So you can see that for every single value of theta, those are actually the same curve, the same graph. Okay, similarly, or not so similarly, for our trigonometric equations, if I were to graph sine 2 theta is equal to cosine theta, well, we can see here sine 2 theta is again in red, but now in my dotted green curve, I have y is equal to cosine theta. So we can see that these only overlap at certain theta values, right? Pi over 6, pi over 2, and looks like also here at 5 pi over 6. All right, so when we only have certain values where these variables create true statements, that's when we have a trigonometric equation, and that's what we're going to be solving for today. So let's hop into our examples here. So we're going to solve 2 cosine squared theta minus 1 is equal to sine theta if theta is in between 0 and 180. So first thing we can do here is move everything with our theta over to one side. Okay, I'm going to move everything with theta over to one side because we eventually want to solve for that theta. And now we're going to use some of our trigonometric identities, and I'm going to substitute 1 minus sine squared theta just to get everything in terms of sine squared. I'm going to substitute that in for this cosine squared theta here. Now when I do that, I can distribute this 2 here and here. So I'll have 2 minus 2 sine squared theta minus 1 minus sine theta. Now I'll go ahead and combine what I can, which is just going to be this positive 2 and negative 1. So now I have negative 2 sine squared theta minus sine theta plus 1. Then I can factor out a negative 1. That's okay. And now I'm going to use a little bit of substitution here. So I'm going to say u is equal to sine theta. And I'm going to rewrite this as 2u squared plus u minus 1 is equal to 0. And using our cross method here, I can find that my factors here are going to be 2u minus 1 times u plus 1. Okay, 2u minus 1 times u plus 1. Now I can put back in sine theta for my u's, and I'll go ahead and I'll use my zero product property. Since I have this factor times this factor, I'm going to set each factor equal to 0. And then I can solve these individually. So I'll have sine theta is equal to 1/2. And I'll have sine theta is equal to negative 1. Now sine theta equals 1/2 on the first two quadrants, because this is quadrants 1 and 2, right? 0 to 180. So the angles that satisfy that are going to be 30 and 150 degrees. Now let's think about the angles that satisfy sine theta is equal to negative 1. Well, to have a negative sign, we need to be in quadrants 3 and 4, right? However, this is in quadrants 1 and 2, so this actually is not going to be a solution for us. Theta does not exist for this factor here. Okay, so my only theta values that create a true statement for this trigonometric equation are going to be 30 degrees and 150 degrees. Now you can verify this by graphing both of these. So if you graph y is equal to sine theta and y is equal to 2 cosine squared theta minus 1, you'll see that you have intersection points here at 30 and here at 150 degrees. Okay, so that's a good way to verify. You can verify that for any equation if you were to just graph each side of your equation separately, you'll see that that's a great way to go ahead and verify where these graphs overlay and where your solutions are. All right, moving on, we're going to solve 2 sine theta is equal to -1 if theta is measured in radians. Okay, so we're going to be working in radians here. Now notice I don't have a certain boundary here for my theta values. Okay, so I'm going to need to find all values of theta, regardless if they're in the first quadrant, second, third, fourth, or whatever. Okay, so to solve this, I'll go ahead and solve for sine theta. So I'm just going to divide by 2, and I get sine theta is equal to -1/2. Now looking at my unit circle here, where do I have a sine value of -1/2? Well, that's going to be right here, right, at 7 pi over 6, and right here at 11 pi over 6, right? And I've got that sine value, that y value of -1/2. Now, keep in mind, though, I'm not given that restriction on what my y or what my theta value actually is. So really, I can go back around starting at 7 pi over 6. What if I add 2 pi to that? And I come all the way around my unit circle again. So any coterminal angle with 7 pi over 6 is actually going to yield a true statement here for this trigonometric equation, okay? And the same thing with 11 pi over 6. Anything coterminal with that is going to hold true. So I can actually add 2n pi to both of these where n is an integer. So if I'm adding factors of 2 pi to both of these, I'm going to come up with a true statement here. So this would be my actual final answer here, 7 pi over 6 plus 2n pi and 11 pi over 6 plus 2n pi. Again, that is because I'm not given any restriction on theta. And if you were to go ahead and if you were to go ahead and graph this, I'll erase these guys, then you can see how we have these repeating intersections, right? It starts here at 7 pi over 6, and then 11 pi over 6. And then if I add 2 pi to this 7 pi over 6, I end up right here at this intersection point. And if I add 2 pi to this 11 pi over 6, I end up right here at this intersection point. Okay, and that's going to go on forever in both directions. All right, now let's solve sine squared theta plus 2 cosine squared theta is equal to 4. So if I were to go ahead and again use my identities, I'm going to put everything in terms of cosine. So sine squared theta, I'm going to substitute as 1 minus cosine squared theta. And then I can combine like terms. Since I have cosine squared here and cosine squared here, I can combine these two terms here and here, right? So this is going to be 2 minus 1, basically. So it's going to be 1 plus cosine squared theta is equal to 4. Now, if I subtract a 1 on both sides, I get cosine squared theta is equal to 3. Now let's take the square root of both sides because I'm trying to solve for cosine theta. Squared cancels with my square root, and I've got cosine theta is equal to plus or minus the square root of 3. Now let's think about this. The square root of 3 is approximately 1.7, right? Now the amplitude of cosine theta is just 1 though. So I'm never actually going to intersect the line y equals 1.7 because my maximum and minimum values are ending there at 1. Okay, so for this we would actually have no solution. And if I were to graph my original statement here, my original equation, what do you have here in green, in the dotted green, is sine squared theta plus 2 cosine squared theta. And then up here in red is the line y equals 4. So you see that they never actually intersect, which means we have no solution. All right, fourth example here. We're going to solve cosine squared theta plus 3 is equal to 4 minus sine squared theta. So I'm going to get, again, everything with my theta on one side. Okay, so I'm going to add sine squared theta to both sides, and then I'm going to subtract 3. I'm going to get everything that doesn't have a theta in it onto the other side. So when I do that, I get cosine squared theta plus sine squared theta. Well, I know that that equals 1, right? That's my Pythagorean identity. So I get a statement that says 1 equals 1. Now, since this is true, this is a true statement, this is actually an identity, which means we have infinitely many solutions. And if I were to go ahead and graph both sides of this equation, okay, you would see that it looks like one graph, when in fact in green, I have graphed the left-hand side of my equation, and in red, I've graphed the right-hand side of my equation. Okay, so those are two graphs overlaid over each other, and you can see that they are the exact same graphs. So we have infinitely many solutions, meaning it doesn't matter what theta value I plug in, I'm going to get a true statement for this equation. All right, last example, looking at our extraneous solutions. All right, so I've got cosine theta over cotangent theta is equal to 2 sine squared theta is equal to 0. So let's go ahead and simplify the right-hand side, or the left-hand side of this. All right, I'm going to go ahead and put cotangent in terms of sine and cosine. So that's going to be cosine theta divided by cosine theta divided by sine. So this is the same thing as cosine theta times sine over cosine, and that's equal to 2 sine squared theta. Now we see here I've got a cosine in my numerator and in my denominator, so those cancel out. And I'm left with sine theta plus 2 sine squared theta is equal to 0. Now I can factor out a sine here. And when I do that, I get sine theta, parentheses 1 plus 2 sine theta, and parentheses is equal to 0. Now using my zero product property, I'm going to set sine theta equal to 0, and I'm going to set 1 plus 2 sine theta equal to 0. So when is sine theta equal to 0? Well, that's going to be at 0 degrees and 180 degrees, assuming we're doing this in degrees. And if I were to solve this side here for sine theta, I would get sine theta is equal to -1/2. Now, when is sine theta equal to -1/2? And if you need some help, look at your unit circle, and you'll find that that happens at 210 degrees and 330 degrees. Now, be careful here. When we use these identities, we need to check our answers for extraneous solutions. So if I were to check here and plug in 0, I'm going to check these two here. If I were to plug in 0, I would have cosine 0 over cotangent 0 is equal to 2 sine squared 0 is equal to 0. Okay, so I just plugged in 0 here for my theta. Now, cotangent of 0. Cotangent is 1 over tangent, right? Now, tangent of 0 is actually equal to 0. So cotangent of 0 is actually undefined, right? Because that means I'm dividing by 0. So if cotangent 0 is undefined, then this whole term right here, that's supposed to be parentheses, this whole term is actually undefined, which means that this is not going to yield a true statement when I plug in 0 degrees. And the same thing happens where cotangent of 180 degrees. That's also undefined, meaning that this is not going to be a true statement. So both of these, 0 degrees and 180 degrees, are not actually solutions. Those are what we call extraneous solutions. Now we can go ahead and test for 210 and 330. And when I plug that in, I get a statement that says 0 equals 0. So if I were to plug in this whole left-hand side into my calculator, you will get 0. You will get 0. If your calculator is in degree mode, you will get 0. So you get a statement that says 0 equals 0. And again, if I were to plug in the whole left-hand side of this equation after having plugged in 330 degrees, again, you will get 0. So you get this statement that says 0 equals 0. Okay, now, again, this did not give me a certain theta value or certain range for my theta. So before I just say that my answer is 210 degrees and 330 degrees, I actually need to think about all my coterminal angles, right? So actually, I can add multiples of 200 or of 360 degrees to this 210 degrees, and that's going to give me a coterminal angle. And same thing, if I add multiples of 360 to this 330 degrees, again, I get a coterminal angle. So my final answer is actually 210 degrees plus n 360 and 330 degrees plus n 360 degrees, where n is an integer. All right, guys, that is it for this video. So be careful about those extraneous solutions. Always remember to check both algebraically and graphically, and good luck with your practice.